Okay, yeah, welcome back. And yeah, let's continue to look a little bit into Axion dark matter and its properties. And yeah, as mentioned also yesterday, from most of what I said so far, whenever I say Axion dark matter, you can already substitute Axion-like particle. It just really means that literally you replace the QCD axion by something that has a much looser relation between mass and coupling. But as you have also seen yesterday, for the production mechanism, there is actually no reference to the coupling because the coupling is assumed to be super weak. So the only thing that entered into the dynamics of our Axion field was really, well, the mass and the field excitation, or how large the field value is. Everything else plays no role. So this is maybe one message to repeat and to actually take home. This production that we discussed yesterday and that will continue a little bit today is completely generic to any type of scalar bosons. All scalar bosons behave in that way. It doesn't matter whether it's a scalar, a pseudoscalar, or whether it's an axion or whatever, some flavored particle, doesn't matter. As long as it's a boson and it's a scalar, it's the same. You could also be tempted, by the way, to use the same thing for a vector. And the second part, the oscillating part of the evolution is exactly the same. That's the part when you have non-relativistic particles, as we have seen yesterday, when you have really dilution like the volume. If you take a vector and you look at the first part, when the Hubble scale is big compared to the mass, that's actually different. Because massless vector fields are massless gauge fields typically, and they have a different behavior when gravity is important. So this is a place where one has to be careful. The expansion behavior of a scalar is nothing is happening, but for a vector, the field amplitude actually drops. So this can be easily missed because it clashes with our intuition of it being particles at rest. But this intuition is actually not good if the Hubble scale is bigger than the mass, as we can already see in the scalar case, because then the density remains constant. It acts pretty much like a cosmological constant, and this is nothing at all like particles being diluted by expansion. So a bit of care when the Hubble scale is bigger than the mass. The equation can still be solved easily, but the intuition is to be corrected a little bit because our intuition is probably shaped by non-relativistic and weak gravity. Okay, before we go into a little bit more detail on the production, let me actually make one comment, and that is it's wave-like dark matter. So what does that actually mean? At the beginning of the week, last week actually probably, it was, yesterday was the beginning of the week. Anyway, so last week you've heard about WIMPs, and those behave like particles. And I'm now going to claim that axions, ALPs, and all those things are so-called wave-like dark matter. So the question is, what does that actually mean? Well, what it means, it behaves like a classical wave. So it's on the side of, well, we're talking quantum mechanics here. We're describing particles with quantum mechanics. It's a quantum theory. That's true for WIMPs as well as for axions. But what we see is, for axions, we get a behavior that is more naturally understood in a wave-like situation. And indeed, it's not even such a very quantum wave, it is even like a classical wave in most cases. But you should maybe remember or understand that the field itself is actually, so to speak, the multi-particle wave function. So whenever we talk about a classical field, it can be viewed to some degree as the classical multi-particle wave function. So in that sense, quantum mechanics is already included, of course, in the Klein-Gordon equation. Klein-Gordon equation, non-relativistic limit, with some trickery. If you want to check it out, for the real field, it's not that trivial. All textbooks do it for the, at least all that I know, do it for the complex field. For the real field, it's true still, but it's slightly funnier. But the classical or the non-relativistic limit of the Klein-Gordon equation is simply the Schrödinger equation. And that's also true for axions, if you wish. And the field variable is really the wave function. So in that sense, whenever we are talking about fields, that's really the kind of wave function picture. Okay, but why is it even a classical wave? Well, when do you get classical behavior? Classical behavior means that you get large occupation numbers. So a typical example where you have that in more or less everyday life, of course, photons or light is described by photons, which you can think of as particles. But if you look at a laser, you have many, many photons explicitly in the same state. And that's why the description of, in a sense, a laser by just a classical wave equation, and you can do that including the cavity and whatever components you have in your laser, is actually a good one. Why does this come about? In principle, you have to be very careful in looking at the classical to quantum transition, look at the right correlators in quantum theory, but roughly speaking, quantum, this is a bit heuristic, admittedly. That means you have occupation numbers and you have the quantum 1/2. So this is the occupation number. And this is a quantum 1/2. Now, if n is much bigger than 1, then 1/2. So in that sense, this is a kind of intuitive picture. When your occupation number is high, who cares about the 1/2? Okay? And that's why in many situations you can easily go from, if you will, quantum to classical, as long as you have this, in a sense, large occupation number. It's a difference between, looking at a quantum mechanical harmonic oscillator that has a tiny excitation, or taking a proper mechanical oscillator and pulling the thing right with it apart, and then you effectively have a huge occupation. It's admittedly a heuristic statement where one needs to be a little bit careful, because at least in theory, I could make a very quantum state by just pulling it, not by just pulling it out, but I could have a highly occupied harmonic oscillator state, which is very quantum in that sense. The way to do that would be to go for an energy eigensystem. Because an energy eigenstate, if you think of a harmonic oscillator, is actually very quantum in some sense. Because if you look at that, the expectation value is 0, despite having a large occupation number. And this is something you don't have classically. Classically, you cannot have a huge amount of energy and basically no excitation of your one-point function or your field. Of course, all the energy is in the two-point function, so it's kind of delocalized in the middle. But this is an exceptional state. So if you typically just pull and go to high excitations, also a tiny bit of observation pushes you into this more classical state. In that sense, this is good heuristic, but one should be aware that one sometimes needs to be a little bit careful. So, bottom line is, what is this occupation number? And let's see what the occupation number is. So, the first thing is that one has to say, it's not everywhere the same. It depends where you are in the universe, at least if you ask for the occupation number today. So let's ask, in a sense, outside galaxies, or more precisely, if no structure formation. This is a bit of an artificial situation. So this is, let me pretend our universe today didn't evolve at all. So we just expanded, and we have our homogeneous or more or less homogeneous initial condition. So all, in a sense, all axions in the observable universe are in the same state. That's what we kind of got after inflation, and if we take it to the extreme. But this completely discards structure formation. This is a bit artificial, but just to get the first number, this gives you then, well, all of them, the whole dark matter mass in the universe, all of them are in the same state. That's what we asked for. So this is rho dark matter, r cubed universe, divided by m axion. And if I haven't mistaken my calculation too much, you get some nice number, 10 to the 88 electron volt per mass. So it's a huge number. So it's enormous. So this is as classical as it gets. So in that sense, this is a wave-like, most wave-like dark matter. But as I said, totally artificial. Can we do better? What we are interested in a sense, is perhaps more in practical terms, what would be the occupation number now and here? Now and here. So what do we need for that? Well, the occupation number is more precisely, occupation number is the number of particles, and I'll make that more precise in a second, per phase space volume. So if I compress a few particles, the number density or the occupation number that we are interested in is basically via the phase space volume. So how do we relate that? Well, so let me just put the phase space volume here. Now, this is actually, we can just kind of bracket differently. We can say this is fairly trivially, I've just split the denominator, but this thing here is nothing but the number density. So this is rho dark matter divided by the mass. And then we have our momentum volume still to take into account. So the important question then is, what is our volume in momentum space? And the volume in the momentum space that we are interested in is just, of course, the volume where you actually are expecting to find particles. So it's, in a sense, the typically occupied momenta that we care about. So we care about the kind of volume that is actually occupied by momenta. And we're simply assuming that they are more or less equally occupied. Okay, so it's kind of an equal distribution. It's only order of magnitude what I'm doing here. Okay, so delta P is the spread of in momentum space and that is the mass times the spread in velocity space. Of course, this is so far just a reformulation, but why does this help us? Well, we kind of know what the velocities that actually can be occupied are. Because the highest velocity that is possible if we are sitting here is the escape velocity of the galaxy. Because anything that's faster will not, well, occasionally one can wander in, but that's not the interesting ones. But typically the bound dark matter particles within the halo should have a velocity smaller than the escape velocity. So this is, and indeed the typical velocity is of the same size. The typical velocity of a dark matter particle is maybe half of the escape velocity, but it's not order of magnitude difference. This just follows from the virial theorem. So if you equilibrate in your galaxy, the typical rotation curve or the typical velocity when you are oscillating like this or taking some ellipse is not much different from the escape velocity, maybe by a factor of 2 or 3. Okay? So we have to ask ourselves, what is the typical velocity, or what is the escape velocity? Well, all that is order of magnitude, roughly 10 to the minus 3, or if you wish, 300 kilometers per second, within factors of 2 or 3. So I think the escape velocity is more like 2 or 3 times that. Our typical velocity around here is the velocity of the sun around the center of the galaxy, which is about 200 kilometers per second. So it's all of the same order. Okay, so we have that. And then we just need the local dark matter density. And that is the same whether it's WIMPs or axions. That's the things that we can measure. We don't know it super precisely. There's some, again, factor of 2 uncertainty range, but the typical number that I find easy to remember is 300 mega electron volts per cubic centimeter. Or, if you wish, 0.3 protons per cubic centimeter. The last one is just for easy memorization or whatever. It's a kind of order 1 proton per cubic centimeter. Okay, so now we just need to take that, plug it in here, take that, plug it in here, and we can do some numerics. And what we find is that the typical occupation number, rho dark matter local, divided by ma to the 4th power, velocity to the 3rd power, is something like 8 times 10 to the 3 electron volt per mass to the 4th power. So, whenever your particle is lighter than an electron volt, you actually get a high occupation number. You get a few thousand already. And it grows rapidly with decreasing mass. So if you're talking micro electron volts, which is not too bad for an axion, we are talking numbers of the order of 10 to the 20 something. So these are properly high occupation numbers, so we have no worries at all when using the classical approximation. So in that sense, classical field theory is the fully appropriate tool to describe this wave-like dark matter. And that is also the reason why it's by now often called wave-like, because then really you can treat it as a classical wave. You can treat it as a classical, kind of more or less even coherent wave in many cases. So it's this is the reason. And just physically, what does this mean, this large occupation number? It means essentially also that within a typical de Broglie wavelength, you actually have many particles. And that means if you think in terms of de Broglie wavelengths, that means they are overlapping. And that means this makes it wave-like. Whereas if you do the same for a WIMP, the calculation still holds. For a WIMP, this number is tiny. The de Broglie wavelength of a WIMP that is heavy is super short. And let's say for a WIMP of whatever, a GeV, the de Broglie wavelength, or let's take 200 GeV, the de Broglie wavelength is a femtometer. Okay, so you have a 200 GeV WIMP. The de Broglie wavelength is a femtometer. Now, with this density, you have such a WIMP per liter, roughly. And that means your WIMP, being 1 femtometer sized, so to speak, doesn't overlap at all with the next WIMP, which is about 10 centimeters or 20 centimeters away, if you're just randomly placing them. So they have no overlap. But if you do the same thing for a micro electron volt axion, the de Broglie wavelength is a kilometer. Okay, so you have a kilometer wavelength, but within this kilometer, say at a micro electron volt, you have, should have calculated it beforehand, 10 to the 6 times 10 to the 9, 10 to the 15, whatever, 10 to the 17, 10 to the 15, 10 to the 23 axions or so, or more. So within that kilometer of the wavelength, you have 10 to the 20-something axions overlapping. So that's very classical. They really have amplitude addition. WIMPs don't. They are nicely localized compared to their wavelengths. That's the difference between wave-like and particle-like dark matter. And of course, this makes life easy because, well, classical field theory is typically a little bit easier than quantum field theory to calculate. You just do put it into the equation of motion. So that's one good thing. But The other good thing is also, if you have high occupation numbers, this is something that one should always keep in mind for detection. If you have something that is a more or less coherent wave, this also allows you to typically have coherent effects. And if you, again, remember way back, at least something I completely ignored when I learned it, things like coherent versus incoherent scattering. People typically make this argument for, I think, light in fog or something like that. Don't ask me to get the numbers right, but the point is that whenever you are doing a scattering, and within your relevant wavelengths, you have more than one scattering center. You have a high density of scattering centers. Your scattering is not proportional to the number of scatterers, but as long as it's coherent, meaning always in the wavelengths, it's proportional to the number squared of scatterers. So you have a much enhanced, coherently enhanced scattering rate. And this is something people use very effectively when doing Axion conversions. You typically have, let's say, if you think in terms of a wave propagating through a medium, say a target, usually you just get probability proportional to length. But if you have coherence, you get length squared. And that's when length really starts to matter and to really help. So you have really enhanced scattering. But it's always n squared, and this is often a very large number. Okay, so that to the properties of this Axion dark matter and why it's also somewhat different to WIMP dark matter. But yesterday there was one final question that we didn't really answer and that I'm only going to sketch now also, but still I think it's worthwhile seeing at least how to do it. And that's what is actually today's dark matter density. And for that, we can actually use something that we learned already yesterday. The density as a function of time is the density at an initial time t1 times the volume of the universe at t1 divided by the volume of the universe at t. At least as long as we are in this weakly damped harmonic oscillator regime. That's the name of the game. We can say a little bit more, also from yesterday. It's the mass of the particle squared. It's the field value at this initial point in time squared. And again, our volume factor. So now, in order to determine today's dark matter density, we need to say something about the initial conditions. And we need to calculate this volume ratio. And this is perhaps the first thing to do, is we need to say something about what is this time that is at least where we can usefully specify an initial condition. Well, T1. So I'm going to give an approximate condition, but of course you can, if you do it numerically, you can do it quite easily much better. But a very useful time to choose is actually when the harmonic oscillator becomes weakly damped, or in other words, when the field starts oscillating. So the time when field starts oscillating. Because before that, this formula is not valid. But the good news is, before that, there is no evolution. So before that time. So in that sense, if we set our time at the time when the field starts oscillating, we can basically take the field value to be either that at this time, or we can also think, this was the field value at the beginning of time. So in that sense, because before that there is no field evolution. Okay, so now, what defines this time? Well, for this we just have to ask let me just try, so also good. We just have to ask, when does it start oscillating? And then you can look a little bit into your harmonic oscillator. Roughly speaking, the time when is set by (3h), which is the damping is of the order of the mass. When this is the case, the harmonic oscillator transits essentially from overdamped to weakly damped. Basically when the damping constant is equal to the mass. After all, that was just the kind of two extremes that we considered. And the transition happens roughly in the middle. If you want to be a little bit precise, and I'll just for the moment include it, just for the purposes of the axion itself, if the mass depends on time, it might make sense to actually also evaluate the mass at that time. And for the QCD axion, the mass does depend on time. And I'll come back to that a little bit later. Okay, so we have fixed our initial time. Then the other initial condition that we can, but of course, in a sense, this is where we have some arbitrariness. As discussed yesterday, the field value is selected randomly, at least in this pre-inflationary scenario that we had, where the axion exists during inflation. We select just one of those random field values. This could be anything. But just to give it a typical scale, it makes sense to say, it's some initial angle, and let me call it theta 1, times Fa. Because after all, the field value goes from 2 pi Fa, or from minus pi Fa to pi Fa. So it has a field range of 2 pi Fa. And it's kind of convenient to parameterize it by an angle, but what we expect is that this angle is not fine-tuned. So just if you throw darts at your circle where your Goldstone boson lives, well, you will typically have an order 1 angle. This is the idea of writing it as an angle. Could be 2 times, could be 0.1, could even be 0.01, but it's very unlikely that it's 10 to the minus 7 times Fa. Could still happen. It's not impossible, but this is the kind of expectation. Okay, so that's our initial condition. We know when to start, and now we just need to calculate this volume ratio. So the only thing to calculate is the volume ratio. Okay, so how do we do that? Well, this is now just a problem of, in a sense, standard cosmology, because we have essentially fixed our time here. So the time is fixed. When we know the time, we know the temperature. and then we know the temperature, then we know how much expansion we had until today. So let's briefly go through that, but I'll be fairly brief, skip a few steps, but roughly speaking, the trick to do is H is determined by 3h squared m Planck squared equals the density. And typically we will be in radiation domination. This is often true, not always. I'm not giving a hint for the exercises here. Dominated universe. At least in standard cosmology. You can always fiddle with the background cosmology if you wish. This is possible. The effects are there, they are noticeable, not super huge, but there is some significant effect if you modify standard cosmology. But I'm going to assume standard cosmology. Then it's typically in the radiation dominated universe. Then rho is something like G star pi squared over 30 T to the 4. And with this, you get that the Hubble scale is something like 0.33 square root of G star T squared over m Planck squared. So now you have related your temperature to your Hubble scale, and at that point you can also easily relate it so for your T1 you can relate it to the temperature to your particle mass. Okay, I need a bit, sponges there. Okay. The first thing to do now, we have our initial temperature, we have our initial time, we have our final temperature. We could be tempted to use something but this is a bit naive. We could say T is equal T0 times A0 divided by A. Then it's a one-line calculation from our initial T1 to our final volume, which is, I should say, scale factor. So this is a scale factor A, but we easily get our volume here. Okay. In that sense, that's actually a decent calculation. You could say even allowing for all the approximations I've made, that's already pretty good. Let's keep it at that. Let me just comment, and in that sense, just comment before giving the final result. Slightly better is to use entropy conservation. Because generally speaking, the number of degrees of freedom in the universe over long times is not constant. For example, electrons and positrons annihilate into photons. This keeps the temperature a little bit higher than you would expect from this equation, simply because you're transferring energy from more species, electrons and positrons into the photons. So that keeps the temperature a little bit higher. So whenever you change your number of degrees of freedom that you effectively have, you have a slight push in the temperature, so to speak. And if you use entropy conservation, that takes it into account. It's also an approximation. You're just saying, I'm transferring, I'm not doing something too violent, so I'm not creating much entropy when doing this annihilation, and essentially, in a sense, transfer the entropy from one degree to the other. But this approximation has been checked, and it's actually pretty good usually. Okay, so if you use entropy conservation, that means that S is equal as 0, A0 over A cubed is S0 volume 0 over volume. So in that sense, it even gives us the cubic factor that we want. The entropy is, however, simply the number of degrees of freedom for entropy. Not necessarily the same as for energy. But the difference is actually, most of the time, also not very big. So I'm just saying this is small factors. 4 pi squared over 90 times t cubed. And now, we are basically in business. We are just using that to calculate the volume ratio. So this gives now a factor that simply differs by factors of this temperature-dependent number of degrees of freedom. There's not more to it. It just accounts for the number of degrees of freedom. Okay, and then we have determined here our starting, so this plus this gives us our starting time, our starting temperature, our starting entropy, and we need the final time. Is today. Then we have temperature of the CMB. That gives us the temperature today. Not much to it. 2.7 Kelvin. And now we just need to insert. What you get now is rho, Axion, is about 5 kilo electron volt per cubic centimeter. This is, by the way, a useful ability, worthwhile practicing, translating things in electron volt. All the things had electron volt to some fourth power, second power, whatever, into something more conveniently used like kilo electron volts per centimeter cubed. You can do a lot of mistakes doing that. I speak from experience. And then you have the mass of the particle divided by an electron volt. So this is just giving the typical scale. I leave a little bit of space. And then you have A1, or A of T1, divided by 10 to the 12 GeV squared, as it must be. This is, after all, just the initial density. It's just this. Times a function evaluated at T1. So, I leave on purpose a little bit of space here. I'll fill it in a second. But let me first of all declare the mysterious f function. And you will justifiably complain about why you use entropy conservation now, because f of T1 is exactly the function that accounts for the degrees of freedom. It's G stars, so the energy degrees of freedom, T1, divided by 3.36. to the power 3 over 4 G star entropy of T1 divided by 3.91 to the power minus 1. And this is just normalized to the degrees of freedom more or less now. This is just, and it's weird numbers because we have not only photons, we also have neutrinos. And that's why actually these two numbers are not the same. Because the neutrinos have a different temperature than photons. So in that sense, they contribute differently to entropy. Okay? That's why when entropy and energy degrees of freedom really split apart, when you have decoupled species. But because it's only neutrinos and there are not too many of them, it's actually not such a big difference. And they also do not decouple too far. The bottom line is, this is somewhere between 1 and 0.3 in a temperature range between now and 200 GeV. So this degree of freedom dependence is not very spectacular, but I nevertheless wanted to give you an impression how to do the calculation a little bit better. But it's in order 1 factor in the other. It's not orders of magnitude. What can be orders of magnitude is the factor that I left out here for the moment. So if you do the calculation as we just did, this is what you get. But if you now allow for a possibility that your mass is changing in time, you get an additional factor. Now I shouldn't have put it away because I think the M1 is in the bottom. Yeah. You get an additional factor, M0 divided by M1 square rooted, where this is the mass, if you wish, at T1. So if your mass is time dependent, you get a different factor for your time dependence. The calculation is pretty much the same. What do you need to do to get this factor? Because so far the calculation did not depend very much on M1. Why shouldn't I write M1 here? After all, I scale the density. But if you look a little bit more closely at your harmonic oscillator with a slowly time-depending pendulum constant, you get a slightly different scaling if you kind of expand or change your thing over time. It's essentially a WKB approximation that you use, and this gives you additional prefactors of a power of the mass at some given time. By the way, it's kind of entropy conservation again, because the produced number of particles roughly stays the same, but in a sense, as you expand, how should I say it? The particle number roughly remains the same, but the mass, and therefore the energy density, changes with your mass. And that gives you also such a factor. Okay, now that's one bit of information. 5 keV per cubic centimeter. Why did I write it like that? Well, rho today observed is about 1 kilo electron volt per cubic centimeter. On average, you should always, if you talk about the dark matter density, there is a big difference if you're talking about the dark matter density here, which we just had, which was 300 mega electron volt per cubic centimeter, or the global average, which tells you we are in a huge overdensity. But bottom line is, this is not far different from here. So if you have initial values in the 10 to the 12 range, masses in the electron volt range, you are in the right ballpark. Or stated differently, if you reduce your mass a little and basically keep that of the same order or make it a little bit bigger, then you will get roughly the right density. The other thing that you see is, of course, this, you are typically free to choose. You're not free to choose it bigger than pi times Fa. That's the limit. But within that, you can always choose. So most of the time, you can match the desired density. Okay, so in that sense, it's if you have decay constants of this order, you get roughly the right ballpark of dark matter. Comment, and I'll go into that a little bit more. For axions, QCD axions, this will depend on time. And it depends on time such that that is bigger than that, is smaller than that. So you push up the density a little. Okay, and let's have a brief look at that because this opens up a little bit of parameter space. QCD dark matter. Well, as already mentioned, A1, A and also A1 are in the range minus pi Fa to pi Fa. So there you have a specific field range. If you wish, theta 1 is an element minus pi. This is simply the angle choice. That's one important thing. But this is true for all Goldstone bosons or pseudo-Goldstone bosons. If you have some random scalar, who knows? Random scalars do not even have a specified decay constant or initial value. This formula would still hold, but yeah, you would be a little bit at a loss what to choose. Maybe you need some mechanism that tells you where you end up in the early universe. But here you have at least some guidance. It's not specific, but you have some guidance where you should aim for. So A1 expected or natural is of the order of Fa. But you can always tune. This is one thing. The other thing is the mass of the axion is actually time dependent. It's the zero temperature or vacuum mass, roughly speaking, for a range of temperatures smaller than the critical temperature, which is of the order of the QCD scale. And I'll say, of course, how it goes. Also for higher temperature, for higher temperatures, it's Tc by T to some power n, and this is for T greater than Tc, and n is approximately something like 8. But this is where QCD models differ. So roughly speaking, if you plot temperature, mass of the axion, it looks something like this. Oh, of course, it's not going to be negative, but it's going down, and this is T critical, which is of the order of the QCD scale. Why is that? Remember, this thing was proportional to m pi f pi over Fa. Fa for low temperatures or reasonably low temperature doesn't change. But we are now in a range where we are talking about QCD effects. M pi and F pi are created by QCD. Indeed, F pi is a scale of spontaneous symmetry breaking of chiral symmetry. So this is the symmetry that is broken by QCD. And at high temperature, you have no chiral symmetry breaking. And high temperature means temperatures high compared to the QCD scale. So if you heat things up beyond the QCD scale, the chiral condensate or the chiral symmetry breaking effects go down, and they go down very, very quickly as a function of temperature. That's why the effective axion mass really very rapidly decreases if you go beyond the QCD phase transition. So at very high temperatures, you essentially have no mass and therefore no evolution. And if you do that, then, well, you can crank your handle again. Determining your m of T1 now becomes slightly more complicated. Well, it's still the same equation, but now you have to take into account the temperature dependence of this thing. But what you get is that rho axion divided by the critical times h squared, which is the usual normalization factor. This is h today divided by 100 kilometer per second in megaparsec, typically 0.7 or something like that. This is just the usual way that cosmologists give this number. It's supposed to be 0.12 or so. So this is the number you are aiming for. And that's some number times Fa divided by 10 to the 12 GeV. And now comes a change that is perhaps the one change that is really slightly surprising, but if you think about it, it's not. In our density formula here, we have the initial field value squared. So we would expect, it depends, this parameterizes somehow naively also the size of the initial field value. So we would expect a square. But because the mass depends on Fa in a non-trivial manner, and the time when this starts depends therefore also on Fa in a non-trivial manner, this power is reduced to 7 over 6 for n equals 8. If you have a different time dependence of your mass or temperature dependence, this power is corrected. So QCD doesn't give you exactly 8, and you can also do all kinds of fit function if you have a lattice calculation, but the order of magnitude is not bad. And then you have your actual initial field value dependence, which is still theta 1 squared. And that's really the square. Of course, it should be proportional to the field value squared. It's these prefactors that give you the non-trivial dependence on Fa. Okay, so it's this bit here and not this one. So, but this, and I should probably specify it, depending how you do the calculation, and I should have picked up some better up-to-date calculation, but this is order 1. It's an order 1 number. But bottom line is, with Fa, you have a slightly weaker scaling. That might be important for the simple reason that if you increase your Fa, which you could think you want to do in some string series. You have, say, 10 to the 15 or so. The scaling in the density is actually not so bad. And indeed, the fine-tuning that you need, which is a square here, is even weaker. So in a lot of older papers, you find a hard limit at some scale about 10 to the 12, because you would overproduce axions. After all, if you increase FA, you get more axion dark matter than you actually observe. That's the overabundance or overclosure limit that people talk about. But the tunings that you require to get rid of that is not very big. So if you allow yourself a percentage tuning, you can go to fairly high FA values and still be happily within the observable limit. So in that sense, overclosure is not a hard limit. It's, I would say, a fairly soft and malleable limit that you can move around. Okay, nevertheless, the message here is FA 10 to the 11 to 10 to the 12 GeV is natural, if you wish. So this is the scale that we should be aiming for. So this is the typical Axion dark matter scale. This is now specific to axions. Otherwise, you have parameters to fiddle with. But for axions, you can always do a bit of tuning. But if you want to really have something really natural without any tuning, that's the right ballpark. And that's why, of course, people are aiming in this region. And if you remember our mass formula from yesterday, this means you have a few micro electron volts in mass. So maybe 10, maybe a bit more, maybe a bit less. But this is the ballpark that you should be aiming for. Okay, how am I doing for time? Oh, let me just make a couple of comments. I will not be very quantitative on that. But following up on the comments from yesterday, so far, pre-inflationary. Axion. That means axion exists during inflation and is not destroyed afterwards. And that means, in turn, fixed but random initial field value. Field value. Zeta 1. That's a parameter of your theory now. Okay, so that's something you do not know a priori. But there is another possibility, so the post-inflationary scenario. And this is simply another possibility. What happens is this is your Peche-Quinn field. Peche-Quinn field. And if you wish, around here, that's your axion. So the goldstone here is the axion direction. And here you have your scale of spontaneous symmetry breaking, order Fa. But that's the T, the low temperature limit, if you wish. At high temperature, typically at high temperatures, you restore symmetries. Your Mexican head potential turns into, well, more or less a parabola with some quartic corrections. That's a generic thing if you crank up temperature. It's not always true, but it's very, very often true, in particular for bosons. So at high temperatures, you have no symmetry breaking. Your axion does not exist. There is no Goldstone boson. And now the question is, if this is the situation at some point after inflation, so if your Paget-Quinn phase transition at some time inflation, you are in this situation. So if your reheating temperature is bigger than your Paget-Quinn temperature, or your phase transition temperature, where you go from this to there, then you destroy your axion. There is no axion at that point. Only afterwards, so no axion. But after T less than TPQ, what happens is you're first sitting here, and then you're rolling down randomly in all kinds of directions. So you're going in all the directions. So you have a random field selection in each causally connected region. So random theta in each causally connected region. So not homogeneous at all. At least if you look beyond the horizon at that time. But the horizon grows. So this really, the horizon at the time, at this time, which is of the order of Fa again, at this early time, the horizon is actually really, really tiny. And as we evolve, the horizon grows actually quite fast. After all, it's the inverse of the Hubble constant, so it goes up with 1 over the temperature squared. So as the temperature decreases, it grows faster than the scale factor, actually. So it's actually growing something like a square of the scale factor for a lot of time. So the horizon really grows rapidly. So what happens as you evolve in time, in a sense, you have some bubbles here. It's a bit of course, oversimplified picture. These are your horizons initially. But as you increase with time, your horizon becomes bigger, and of course, you are seeing more and more of these patches. So as time increases, you're seeing more and more of these patches. And as you increase further and further, the patches individually grow, but your horizon grows faster. That's the important point, to see more and more of these patches. And when this happens, you can start asking, we were interested in the global density. and that's a global average density. We look for average density. And the average density is now quite easy to get because the average density is given by A1 T1 squared, and this is of course something like FA squared over 2 pi, and now we are averaging over all possibilities to randomly pick some initial value for theta. So we're just averaging over this squared, and this is nothing but pi squared over 3 FA squared. So you just do this average. You have no choice anymore. Because you did random choices in each patch. So you could have, say, minus 1.1 plus 0.2 or something like that. But you do that enough times, you choose enough, you end up with the average. So density fixed. So that's a pretty good news. So once you have done that, you plug it into your formula, or in a sense the Axion formula that I unfortunately already erased. You plug it in there, density fixed. When the density fixed, you match it to the precise measurement from the CMB, and you have your mass fixed. You're set up for your experiment. So MA fixed. The only problem is, so this would be perfect news. You have your one mass, and that's what you go and target experimentally. You could still be in the pre-inflationary scenario. That's a 50-50 chance, as much as you want to assign chances. This is, of course, completely random in model space, but you could go for that. You would have this super precise prediction. Without going into details, because I want to comment on one detection method at least. The problem is strings and other defects. And the reason is sometimes it happens that when you do this kind of minus pi 0 or whatever, minus pi half, whatever, pi half pi. If you have patches that are neighboring like this, and you see you go around the Axion initial field once. This is a weird place. Here you touch minus pi and pi. It sounds weird, but it isn't, because actually the field doesn't care, because minus pi is not a special point. You can always go, you shift your field by 2 pi, or your angle by 2 pi. It's the same. You just completed a circle. This is the same, but you went around once. And if you look at it, in the complex Peche-Quinn field, it looks as if your phase around this point was doing something like this. Your complex field was doing something like this. It's like this hedgehog structure. And that's a topological defect. This is stable. It's very hard to kind of contract a field configuration like this to 0. Okay? And such a configuration contains a lot of energy, but it's fairly stable. And this can happen. You know, you just do random things in your different patches, you get a situation like this. So you form a string. String goes through your whole observable universe for a while. It's not stable because it actually costs some energy to go around, because there's a little bit of offset here at late times. So you're a bit tilted, so it decays. But now, the decay, well, that's hard to calculate. And it depends exactly on how it decays. Because as you decay, you radiate off axions, and it depends on the spectrum of these axions, how much density you actually get. Because if you have lots of high energy axions, you put a lot of energy into kinetic energy. But kinetic energy is rapidly redshifted away. What counts is the number of axions that are produced. So from the same energy in your strings, you can produce a few high energy axions or a lot low energy axions. The final density is dependent by the number of axions you produce, because the kinetic energy is redshifted away. So you need to decide which happens, and that's numerically just a horrible problem. So people have employed hardcore computing, and they disagree by factors of 10 or 100 or how much energy this contributes. So in that sense, I should put a big question mark here. It's not that fixed, okay? But this is not something, it's not fixed by the theory. The theory would tell us. It's not fixed by our inability to make a good calculation, okay? Good. I guess I have only a few minutes left, yes. Okay. Very good. So much for the production and generation of axions. But let me spend at least the final few minutes on detecting axions. So, there are good news when you have axions as dark matter. The signal of detection is proportional to the number of dark matter axions, so the number density of axion dark matter. So if you have more axions, or a higher density of axions, your signal goes up. That's fairly generic. That's what you would expect. If you have more things to detect, great. And it's proportional to the coupling squared. The coupling is small for axions. After all, they're supposed to be dark matter, they're supposed to be relatively weakly intact. So it sounds like this is bad news, but this is actually good news, because this is for a dark matter experiment. If you had a lab experiment without dark matter, you would have a coupling squared for the production, because if you now want to do it in the lab without relying on dark matter, you have to produce your axions. That costs you a coupling squared times the coupling squared for detection. And now you have coupling to the fourth power. So in that sense, if you have a pure lab experiment, you're suffering from, well, 2 extra powers of a really, really tiny coupling. So that's why dark matter experiments are typically way more sensitive than non-dark matter experiments for these weak couplings. So in that sense, more sensitive. This is completely generic. You're simply relying that you have already a huge number of particles to detect. Okay? So you heard last week about WIMP detection. So WIMPs bumping into xenon or something like that. You heard about that? Any suggestion why I can't do that with axions? Why can I not bump my axion into my xenon nucleus and hope for a detection? Yeah? Exactly. So there's super light. If you bump into it, you wouldn't notice. The energy transferred goes down significantly with the mass of the particle, and indeed, it's actually mass of the particle squared. So your signal, and you need a certain threshold, so the energy transferred is essentially zero. So no chance to see that. But you can do something much better. You can use the photon coupling. If you have a coupling like that, and let me already write again. This is E dot B. You have a Feynman diagram. That's typically very easy. You have an axion, and you have a photon, and you have another photon. Okay? Now, you can ask yourself, I could wait for this thing to decay. You can easily check that if your coupling is weak and your mass is small, you wait forever. So axions are not a stable dark matter candidate, but that lifetime is very, very, very long. We are not talking lifetimes of the universe here, we are talking 10 to the something lifetimes of the universe. So it's sufficiently stable. And the smaller your mass, the slower and really very rapidly, it's like a third power of the mass, your decay rate decreases. Okay, so waiting for a decay, you can do it. So some people look for it with telescopes, but for the microelectron volt masses, no chance. But you could say, I have my plenty of dark matter axions. I'm in a lab, so let me provide a target for them with many photons. And a target with many photons is a magnetic field. They're not real photons per se, it's more like a virtual photon, but it's photons. So you can provide a magnetic field, or if you think in terms of classical equations of motion, you're providing here a background B. And I'm providing a big static magnetic field. So in that sense, plenty of target photons. And my axion wanders in, and out comes a photon. My axion has an energy EA. What's the energy of the axion that comes in? Any suggestions? Lowest order. It's a dark matter axion, and we are sitting here in our galaxy. Lowest order suggestions. It's just after lunch, I realize that. It's the mass of the axion. After all, it's a non-relativistic particle. Most of its energy is in its mass. If you want a correction, it's 1 plus v squared over 2. That's the kinetic energy. All higher order corrections, completely negligible. Okay. What's the energy of my photon? Any suggestions? Let me comment again, it's a static magnetic field. Exactly. Because a static magnetic field, in quantum mechanics, energy is always linked to time dependence, and a static magnetic field has no time dependence, so it can't provide you with any energy. So this does not give any energy. So energy conservation dictates photon energy equals axion energy. So it's mostly Ma, again 1 plus v squared over 2. So that's good news, because this is small. After all, that's again the velocities of all the dark matter particles zipping around. So this is basically all photons that come out have the same energy. So it's a monochromatic peak that I'm looking for. So it's more or less monochromatic peak. And that's always easier to look. If you look for one energy, a nice peak over background, that's experimentally a much better signal. So that's good news. You have a little bit of width of your peak due to the different velocities, but it's small. Okay? And that's what you need. You provide a super big magnetic field and look for photons. You actually have done something that is much different from WIMP detection. WIMP detection, you're detecting the kinetic energy of the WIMP. Here, you're detecting the total dominated by the mass energy of the axion. So you are actually, and this I always find a bit funny, but also very nice, you're actually converting dark matter into electricity, because photons are electricity essentially. And you're doing 100% conversion. So all the energies that flows to your detector and that you manage to convert, that's the caveat, goes into electricity. And you can calculate in the exercises how much electricity you can generate. Okay, unfortunately, the probability of this conversion to happen for ordinary magnetic fields is not that big. So you employ another trick. And the other trick is, again, you're using it's monochromatic. They have all the same oscillation frequency. You can use a resonator, or more precisely a cavity, to enhance the signal. Why? Roughly speaking, if you look at your equation of motion for your electric field, with such a coupling and a magnetic field background, the axion drives an oscillating with frequency MA electric field. And if your cavity frequency is approximately MA, well, if you're driving a cavity and the electric field inside your cavity with a frequency that is equal to the driving frequency and your resonance frequency of your cavity, the signal goes up. And that means you get a factor of the quality enhancement. Quality or resonant height. So the quality or the inverse damping factor of the cavity tells you how big your excitation is going to be if you're on resonance. And the better your cavity, the higher your resonance. And you get this factor of a Q enhancement in your power output. And this, if you choose a good cavity, can be easily a factor of 10 to the 5. So this is why this is a useful thing. A couple more comments. I can't go into much detail beyond that. You cannot go much beyond this 10 to the 5 here for two reasons. First of all, if you make your cavity better, if you make your resonator, generally speaking, better, the resonance becomes narrower. And you still want all your photons to be within the resonance, otherwise you're not driving effectively. And this is the width of the peak. And the width of your cavity should be at least as big as the width of your peak. So that's reason number one why you don't want to go to Q 10 to the 11 or so. 10 to the 11, by the way, is possible for a cavity resonator in this frequency range, or in the desired frequency range. The other problem is this B field. Because a 10 to the 10 or 10 to the 11 cavity is superconducting. Any suggestion what happens if you put a superconductor into a magnetic field? A very strong magnetic field. You have two options. Either your magnetic field is repelled. It doesn't enter your superconductor. You basically, in a superconductor, magnetic fields are damped. The other option is your field is bigger than the critical field strength. Then it penetrates. But then your superconductivity is gone. Both are not really practical options. Nevertheless, people are playing with some combinations and funny geometry such that you can penetrate on one side, have superconducting on the other. But that's what people are doing. And the final comment is, roughly speaking, just to give you an idea of what people are doing. So microelectron volt or few microelectron volt masses are frequencies in the megahertz to gigahertz regime. So if you go through the masses, you're in this kind of frequency regime. Hundreds of megahertz, tens of megahertz. I should probably not have mu eV to millielectron volt or point something microelectron, somewhere in this ballpark. So this is the ballpark where you would have axions. This is this regime, and you probably, for photons, this is a fairly well-known regime. That's radio frequencies, that's radar. You have fantastic technology. You can listen to a radio, you have radar, so people invested a lot of money into this technology, so you have fantastic detectors. The other thing is, you can calculate your power output, and that turns out to be something like G squared A gamma gamma, volume B squared, or cavity, density of axions, some constant, 1 over the mass of the axion, and some Q factor. Now, if you put in some typical parameters, it's 10 to the minus 24 watts for couplings of 10 to the minus 15 inverse GeV. So that's the 10 to the 12 axion scale. So that's the typical thing you would expect for axions, and whatever, over 5 Tesla, squared and a volume over 5 liters squared, linear, and a Q of 10 to the 5. And a mass of 20 microelectron volt. So, but just to give you an idea, 10 to the minus 24 watts. That's what people get out. But this is not bad. This is something you can detect. This is the amazing thing about radio frequency technology. This is visible. If you increase your power, it's easier to see. That means you are faster. But bottom line is, this is detectable. This is what ADMX is looking for right now. I hear some persistent rumors, so if someone has some more information, that there's some vague rumor about ADMX having something, but I haven't heard it. Or heard details. I've heard the rumor, but not the details. Oops. I didn't say anything. I only hear rumors. I have to say second or third hand rumors. Is doing that. And let me just say, they could see theoretically they're in the sensitive region, so that's why it's interesting. Okay? Okay, I think I'm pretty much out of time, but I think this is also where I wanted to get to. So bottom line, axions are ALPs are a quite cool dark matter candidate. Interesting properties like wave-like dark matter. So it's really different from the particle-like dark matter. Different production mechanism. As we've seen, just some coherent initial field values that then produce your axions. But a fairly natural one. It's something you can't switch off for bosons. That's an important thing. And then you have predictive properties, and well, you have ways to detect them. This is not the only way, but this is perhaps at the moment the one closest to being able to see something that is truly a QCD axion. Okay, I would say let me stop here. Thanks.